3.4 Properties of Logarithms. So now we're really getting into the fun stuff. At least in my opinion, this is the fun stuff. This section and the next section, all fun stuff that have to do with logarithms. So let's talk about a few properties of logarithms. We've already mentioned these before, but I kind of want to put them together formally. So let's get a pen here. 1, log base b of 1 is equal to 0. It doesn't matter what your base is, that's always going to be true. So as an example, if I have log base 3 of 1, that would be 0. And the reason for this, if you do the loop-de-loo, right, so if I take the base across the equals back again, you would get 3 raised to the 0 equals 1, which is a true statement. Second property, log base b of b is equal to 1. So as an example, if I had log base 2 of 2, this would be 1. And it'd be 1 because, start at the base across the equals back again, 2 raised to the 1 is equal to 2. And this will be true regardless if it's 2 or 3 or 4, whatever your base is. If it's raised to the first power, it's just going to give you itself. So log base 2 of 2 is equal to 1. Number 3, b raised to the log base b of x is equal to x. As an example, we could have 2 raised to the log base 2 of 5, and this would all be equal to 5. You can kind of think about it as the 2 and the log base 2 cancel, and you're just left with this 5 here. Let me undo that. But if you think about the loop-de-loo thing, start at the base across the equals back again. So this whole thing is the exponent. So it's log base 2, right? Start at the base across the equals, we get 5, is equal to the exponent, which is log base 2 of 5. So yes, log base 2 of 5 is equal to log base 2 of 5. So that would make sense that that rule works. Last property for this round of properties, we have that log base b of b raised to the x is equal, that's a bad equals, is equal to x. So in the same way that up here the b and the log base b kind of cancel, it's like the log base b and the b cancel here, and they leave you with just that exponent. So as an example, log base 3 of 3 raised to the 7 is just equal to 7. And if we do the loop-de-loo, start at the base across the equals back again, this whole thing is on the inside, by the way. So this whole thing is on the inside. So at the base, 3 raised to the 7 is equal to the inside of the logarithm, just 3 raised to the 7. So yes, that's a true statement there. So it's like, where's my pointer? It's left this log base 3 and this 3 here just canceled themselves out and left us with that exponent up there. Only works if these two are the same. Can't do it if they're not the same. So let's do an example or 2 or 3 using those properties. So we're going to find the exact value of the logarithm using the logarithmic properties listed back here. Why don't I pause it and rewrite the properties on this page real quick. All right, so we have these properties written over here now. All right, so we want to find the exact value of this logarithm here. Now I'm going to be a little bit tricky here. The 9th root of 3 can be rewritten in its exponential form as 3 raised to the 1/9 power. So the 9th root of 3 is the same thing as 3 raised to the 1/9. If you remember from Math 96, I believe, if you have x raised to the m over n, this is the same thing as the nth root of x raised to the m. This might be an important fact for later, so definitely keep that in mind. Here, we didn't have an exponent on the 3, so the numerator is 1, and then the root is 9. So then root is always the denominator of the fraction in the exponent. But now looking at this, it's log base 3 of 3, and we talked about this. It's like these log base 3 and the 3 cancel, and you're left with 1/9. And that's by, right over here, rule number 4. All right, so looking at a different one. ln of e to the 6th. So if I come back to my list over here, each of these log properties can be rewritten with the 2 special bases. So there's log base 10 and then there's log base e, which is just ln. So we could write the special versions here. If you don't have a base written, it's base 10, so log of just regular 1 is equal to 0, and ln of 1 is equal to 0. Remember, ln of 1 is the same as log base e of 1. Here, we could say log of b is equal to 1. And we could say ln e is equal to 1 because, once again, this is log base e of e. So ln e is equal to 1. Down here, with base 10, so 10 raised to the log x is equal to x. And for ln, we're looking at e raised to the ln x is equal to x. Finally, down here, we have log base 10 of 10 raised to the x is equal to x, and ln of e raised to the x is just x. So those are the special versions, mostly these guys over here. That's kind of the special one, because the notation is so much different. But they're all the same properties because they're all logarithms. So let's go back over here, and we have ln of e raised to the 6th. So looking at this guy right here, it's instead of an x, it's a 6, right? We can think of it as the ln and the e just kind of canceling. So the ln and the e cancel, and left with just 6. And this is also by this rule here. It's this rule, but in the version of ln. Let's look at something slightly harder. So log base 2 of log base 1/2 of 1/4. Right. So we need to figure out what the value of this logarithm is. It's clearly a very complicated logarithm. Now, we're not going to use our calculators. We're going to do this by hand. So we're going to do the thing that we've done before where you set this equal to y, and then we just try to solve for y. But we start by making it into its exponential form. So this whole thing here, that's an awful box, but that whole thing there is on the inside of the first logarithm. It's on the inside of this guy right here. So when we go to do from the base across the equals back again, this whole thing is the back again part. So start at the base, across the equals, back again. We could rewrite this as 2 raised to the y is equal to log base 1/2 of 1/4. Now, over here, we can try to simplify this, right? Log base 1/2 of 1/4. We'll set it equal to, I don't know, w, it doesn't matter. And then do our loop-de-loo, and we're just going to find this value. So we have 1/2 raised to the w is equal to 1/4. Well, if you square 1/2, you would square the top and the bottom. So 1/2 squared is equal to, not 1/2, is equal to 1/4, which means that w has to be equal to 2. So this whole thing here was w, right? Because we said log base 1/2 of 1/4 is equal to w. So this whole thing right here is w. And then we decided that w was 2. We're now at a point where we can solve for y. So 2 to the y is equal to 2. 2 has a secret exponent right here. So that means that y should be equal to 1. So the value of this entire logarithm is 1. So I guess I don't need to write y equals 1. This is just equal to 1. If we want to talk about a slightly different way of solving this problem, I'll just try to erase as beautifully as I can. So remember, where's my pointer? Let's see, here we go. Remember that this thing right here, when we found w, that this was equal to 2. Ooh. This was equal to 2. So we could rewrite this as log base 2 of 2 and use this rule over here that says if you have log base b of b, it's equal to 1. So we could just say this is equal to 1. And this would be rule number 2. So 2 different ways to do that. So there's more properties of logarithms to bring up. And I would say that these ones are the more exciting properties of logarithms. So our fifth property, this is going to look weird, is that if you have log base b of x raised to the c, you can take this exponent and bring it down in front. And you would have c times log base b of x. So you can take the exponent down into the front. As an example of this, if I have log base 4 of 5 squared, just trying to find my pointer, I can take this 2 and put it down in front and get 2 log base 4 of 5. The two special versions of this, they're not going to look that much different. If you have log of x raised to the c, this is c times log x. You're just not writing the base because it's base 10. Or the ln version is ln of x raised to the c is equal to c times ln x. So it doesn't work any different with the other bases. So just thought I'd mention that. The other thing to mention is it's really important that this exponent is within the logarithm. So note, the exponent must, let's squiggly line that, must be within the logarithm in order to bring it down. So you might say, well, how do I know that the exponent is within here? Ideally, there would be parentheses written here, but oftentimes there's not. So you can assume that this exponent is within the logarithm if it's written like this. The time where you can't make that assumption is if you had parentheses specifically on the outside here. So see how this exponent is clearly not on the inside of the logarithm, it's clearly on the outside. So this would not be equal to 5 log 7. See, this is not equal. Let's just erase that. I'm not going to write is not equal. I'm going to need this space down here. So that's special. Keep that in mind. It doesn't happen frequently, but it's an important rule to know. All right, second to last rule. If you have log base b of a times c, that multiplication on the inside can turn into addition on the outside. So you can split this up, it's going to look weird, into log base b of a plus log base b of c. So multiplication on the inside means you can separate the logs with addition on the outside. And with the other versions, with the other bases, same idea, log of a times c is equal to log a plus log c. ln of a times c is equal to ln a plus ln c. As an example, let's say we had log base 2 of 3 times 5. We could break this up into log base 2 of 3 plus log base 2 of 5, because 3 and 5 are being multiplied on the inside. Remember, I'm keeping my base. They keep the same base there. Final property of logarithms. If you have log base b of a divided by c, well, if multiplication turns into addition, one might hypothesize, and be correct in hypothesizing, that division on the inside turns into subtraction on the outside. So this turns into log base b of a minus log base b of c. For the other bases, same thing. So log of a divided by c is equal to log a minus log c, and ln of a divided by c is equal to ln a minus ln c. As an example, let's say we had log base, 16 of 7 over 11. We could break this down into log base 16 of 7 minus log, I'm going to run into things. Let me just take all this, and the beauty of doing this on an iPad, move that down and only do a bit of damage. Sorry, log base 16 of 11. So those are our important properties of logarithms, and now we're going to do fun stuff with that. All right, so on each of these problems, I have put a condensed version of the rules over here. It doesn't have the different base options, but it's enough to reference while we're looking at it. So we're going to use the properties of logarithms to evaluate each of the following expressions. So we have 2 different expressions here. The first one, if I'm looking to evaluate this, I don't have any rule that could help me simplify log base 12 of 3, same thing over here, but I could use this guy here. I see it as a number out front. Now, if we do the backwards version of this one, if you have a number out front, you can bring it up to the exponent. So I'm going to start by taking this guy and bringing him up to the exponent using rule number 5. So I'm going to leave the first part alone, log base 12 of 3 plus log base 12 of 2 raised to the 2. Once again, rule number, 5. So now, still nothing happening, but I could combine together these two using rule number 6. So if they're being added on the outside, I can go ahead and take each of these numbers and multiply them on the inside. So it'll still have the base 12. We'll have 3 times 2 squared. Once again, that was using rule number 6. Right. This number right in here is 3 times 4 because 2 squared is 4. So this is 12 in here. So log base 12, 12 of 12. And if we look at our list again, log base 12 of 12, log base b of b, that's going to be equal to 1. And that would be by rule number 2. So by the magic of iPads, I'm going to take this, move it a little bit down so we have some room here. Now, up here in this first problem, we couldn't do anything to simplify either of these pieces as they were. However, we can do something here. So if you remember, let's see, not that rule, this rule right here. So log base b of b to the x is equal to x. We said that the alternative version was ln of e to the x is equal to x. So these ln e's can really cancel, and you're left with just the exponent. So this is 11 minus 7, and that's using rule number 4. And 11 minus 7 is 4, and that's your answer. Let's go ahead and try again on this guy. Now he looks a little nasty, but we just kind of have to focus on what we have. So this 5 is the base, and then all of this is in the exponent. So we have 5 raised to the log base 5 of 6 plus log base 5 of 7. Neither of these can be simplified in the form they're in, but we can use this rule number 6 down here to, because it's adding on the outside, bring them together as multiplication on the inside. So let me rewrite this. 5 log base 5 of 6 plus log base 5 of 7. And then I'm bringing together those logarithms in the exponent. So now it's log base 5 of 6 times 7. And that was using rule number 6. So simplifying that, we have 5 log base 5 of 42, because 6 times 7 is 42, just simplifying. Now, looking at our rules over here, well, rule number 3 says if the base is raised to a logarithm with the same base as the exponent's base, then they could just cancel and you get whatever's inside the logarithm. So essentially, the 5 and the log base 5 cancel, and you're left with 42. And that was by rule number 3. So you're going to see a problem like this one on Alex. It's going to ask you to fill in the missing values to make the equations true. And you're really just using these properties over here and putting in whatever makes sense. So, let's see. It looks like we have addition between two logarithms that have the same base, and addition between two logarithms with the same base turns into multiplication on the inside. So we should be multiplying 2 times 7, and that would give you 14. Make an arrow here. This is because it's 2 times 7 on the inside there. Down this guy here. All right, well, subtraction between two logs with the same base looks like it turns to division on the inside. So it's the first, the inside of the first is the numerator. The inside of the thing you're subtracting is the denominator. So 7's on top and 3's on bottom, which means that this should be 3. Because when you combine it together, you'd get 7 over 3. This next one might take a little bit more work. So we have log base 3 of 1/4 is equal to something out in front, log base 3 of 2. Now, I should just kind of call this guy, I'm going to call him x, and we're trying to solve for x, right? That's what we're going for. So I know that I can bring the x up to the exponent here, and the equation would become log base 3 of 1/4 is equal to log base 3 of 2 raised to the x. Because both sides have a log base 3 and it's just a log base 3 and then something inside, it would be necessary for, if these are equal and the log base 3's are the same on both sides, these insides have to be the same as well. So it would have to be true that 1/4 is equal to 2 raised to the x. Now, you have to be a little bit tricky here. I need to somehow get 2 into the denominator so that I can write them similarly. I can get 2 into the denominator, or I can find a way to rewrite 1/4 so that 2 is the base. Now, that sounds a little bit better. So I'm going to take this 1/4 and let's talk about how we can rewrite it. We'll just take it off to the side here. So 1/4 is the same as 4 raised to the negative 1, right? Negative exponents put something in the denominator. And I know that 4 itself is 2 squared. If you have exponents outside like this, you can multiply them together. So this is 2 to the negative 2. So instead of 1/4, I'll write 2 to the negative 2 is equal to 2 to the x. And then these exponents have to be equal. So negative 2 is equal to x. So if I erase this and put a box back there, this should be negative 2. All right. So we're getting into some topics that are incredibly important for those of you going into calculus. There's 2 things about logarithms that come back hard, and that's expanding and combining logarithms. We're going to start with this idea of expanding them. So expanding a logarithm means you separate it into as many pieces as possible and you bring down all the exponents. Conveniently have that written right here. So you separate into as many pieces as possible and you bring down all the exponents. So let's go ahead and look at this guy. We have log base 9 of x squared times the square root of 3x minus 5. And I know I can use rule number 6 over here to take multiplication on the inside, because even though it's not written, these are being multiplied. I can take multiplication on the inside and turn it into addition on the outside. So I have log base 9 of x squared plus log base 9 of the square root of 3x minus 5. Now we are not done here. There are still some exponents we can bring down. One important one to talk about, the square root of 3x minus 5 can also be written as 3x minus 5 raised to the 1/2 power. So square roots can be written as 1/2 powers, if you'll recall from Math 96. So if I rewrite as, we'll leave the first part alone, we'll rewrite this inside part as 3x minus 5 raised to the 1/2. Then you can see we have these exponents that we can bring down in front using rule number 5 here. So if it's an exponent on the inside of a logarithm, we can bring it down to the front. So we have 2 log base 9 of x, and he loses his exponent because we brought it down in front, plus 1/2 log base 9 of 3x minus 5. So he loses his exponent as well because it's out here in front. And that is as many pieces as we can break it into. We can't break this up anymore because you have to have either multiplication or division on the inside of a log in order to break it up. So we can't break up him anymore. This guy's broken up and all of our exponents are down. So that is our answer. That is our fully expanded logarithm. So we're going to do several expanding examples. Let's look at our next one. So expand the logarithm, and we have ln of x plus 4 raised to the 5th all over x cubed. So since we have division on the inside of a log, rule number 7 here says we can separate it by doing the numerator minus the denominator, log base b of it, you know, just shortening what I'm saying out loud. So let's start with ln of x plus 4 raised to the 5th over x cubed. And I'm going to take the numerator, x plus 4 raised to the 5, and then minus ln of the denominator, which was x cubed. Now I can bring those exponents down into the front. So we'd have 5 ln of x plus 4 minus 3 ln of x. And that's as far as I can break it down. So you can only break it down further if there's multiplication or division happening. If there's no multiplication or division on the inside here, like this is x plus 4, you can't break it down any further. So that would be done. So this example looks a little harder. It looks a little messier. It's going to be a little more tedious, but it won't be awful, just more tedious than anything. So I'm going to start, when I look at this, ooh, that's not my pointer. When I look at this guy, I think it would be easiest if we started by doing the division part. So we have this stuff in the numerator and this in the denominator. So I'm just going to write an equal sign over here because it's going to take up a lot of space here. So I'm going to do log base 4 of the numerator, so 16 times x minus 5 raised to the 6th times the cubed root of x minus 2, and then minus log base 4 of the denominator, which is x cubed. I'll worry about bringing his exponent down in a minute. I want to break up this guy here, and there's actually a chain of 3 things being multiplied. 16 is being multiplied by x minus 5 to the 6th. It's also being multiplied by this cubed root. This cubed root we need to rewrite as an exponent. So let's do that first. So we have x minus 5 to the 6th, and then x minus 2 raised to the 1/3 power. So 1/3 is the same thing as the cubed root, minus log base 4 of x cubed. So let's start with taking the 16, and we're saying that 16 is being multiplied by all of this stuff. So this is our A and this is our C. So we're going to separate it using, not that rule, this rule here, rule number 6. So we have log base 4 of 16 plus log base 4 of x minus 5 to the 6th and x minus 2 to the 1/3. Minus log base 4 of x cubed, which is sitting right out here. Let's write that a little nicer. X cubed. Right. Now we have these 2 things being multiplied, so we'll split those up. So log base 4 of 16 plus log base 4 of x minus 5 to the 6th plus log base 4 of x minus 2 to the 1/3 power minus log base 4 of x cubed. So we're almost there. I promise I'm going to talk about a shortcut to this. It won't actually take this long in the future. You'll be able to do this in one step, but I'm going to kind of walk through the process a few times just so that you can see how it all happens. All right, so I have these exponents I can bring down in front. I have log base 4 of 16 plus 6 log base 4 of x minus 5 plus 1/3 log base 4 of x minus 2 minus 3 log base 4 of x. And this might look done to you. And it's deceiving that it looks done because this guy over here can actually be simplified a bit. So log base 4 of 16 is the same thing as log base 4 of 4 squared. And the log base 4 and the 4 cancel because of this rule, or not that rule, let's see. This rule, right? Nope, this rule. Right here, where the base and the b right there, they cancel, and you're just left with the x. So we're just left with this 2 here. So this guy right here is actually 2. So why don't I just kind of erase this and put the 2 in right here. And that right there, my friends, is our final answer. Next example. So again, expanding still. We're going to do quite a few expanding. So we're looking at expanding this, but it's different because we have this radical on the outside here. If you have a radical that surrounds everything inside of your logarithm, it's just time to rewrite this. So we'll rewrite it. There is no base written here, so you're assuming it's base 10. This is not part of the base, that's just part of the root. Being raised to the let me stop. Taking the 4th root of something is the same as being raised to the 1/4 power. So this is the same thing as x squared over y z to the 8th, all being raised to the 1/4 power. There are so many different directions you can go at this point. You can bring that 1/4 down in front. You could distribute the 1/4 to each of the exponents. Any of those are going to work. Why don't we go ahead and do the bringing down the exponent first version? So we are taking this exponent and we will bring it down in front. So we have 1/4 log, so just want to make it look like a 4, 1/4 log of x squared over y z to the 8th. All right, here's the thing we have to be really careful of. So we're going to separate this. We'll separate by division first. We have to be careful because when we separate it, the 1/4 belongs to both of them. So we're going to need to use parentheses here. So the 1/4 is on the outside, and then I'm separating it. So it's going to be the numerator, so x squared, minus log of the entire denominator, so y z to the 8th. This 1/4 being outside of parentheses is incredibly important because it gets distributed to both of them. So keep that in mind. Our next step here is breaking up this guy. We have to be careful because there is a minus sign right here. So once again, parentheses will be very important. So we have 1/4 log x squared minus, and then we'll do parentheses because we're going to split this up. So log y plus log of z raised to the 8th. We're going to do a little simplifying here. So I'm going to distribute this negative sign to begin with. Next, we're going to bring down those exponents. So the 8 will come down, log y doesn't have any, this 2 can come down. So we have 1/4, 2 log x minus log y minus 8 log z. I guess I'll bring this up because sometimes this question does come up. I'm using brackets here and not parentheses just because it helped differentiate that there's two different types of parentheses being used. The brackets aren't anything special. It's really just the same as parentheses, but they look a little different so that you can tell the difference between them. All right, and then the last thing I'm going to do, I'm going to distribute this 1/4 to everyone. So 1/4 times 2 is going to give us 1/2. So maybe I'll write it as 1/4 times 2 is 2/4. Maybe I'll write it as this and then simplify so that there's no confusion on where things are coming from. Minus 1/4 log y minus, this is 8 times 1/4, so 8/4 log z. 2/4 is the same as 1/2, so 1/2 log x minus 1/4 log y minus 2 log z. And that is our final simplified answer there. Now, as a note, up at this step right here, you could have distributed this exponent. I mentioned it briefly. You could have distributed the exponent. And when you distribute it, you multiply exponents. So this would be log of x raised to the 2/4 over y raised to the 1/4, z raised to the 8/4, because you're multiplying. And then if you simplified, you'd have log raised of x to the 1/2, y to the 1/4, z to the 2, and you could have simplified from there and you would get this exact answer here. So I told you there was a shortcut and I want to start talking about that. So let us go back all the way to our first one. I want us to start comparing our final answer to where we started. So down here in our final answer, there was no denominator, right? And this was positive, there's a plus sign here, everything was a plus sign. And it's the 2 got brought down in front here, and then the exponent on the 3x minus 5 got brought down here, and that was our final answer. I promise this will start to come together. Here's what we started with. Here's our final answer. Notice that the thing in the numerator was positive, and then the thing that was in the denominator is negative, and then it's just the exponents that are brought down. So the 5 gets brought down in front for this guy, and the 3 gets brought down in front for this guy. Looking at this guy, everything is positive, right? It's positive 2, plus sign, plus sign. All of that's positive except for this last negative here. This last negative comes from this one thing in the denominator, and it's just his exponent is brought down. So we have the x minus 2, his exponent is 1/3, that's out front. The x minus 5 had the 6 out in front, and then this 2 here was because log base 4 of 16 is 2. Looking at this guy, there were 2 things in the denominator. Those 2 things ended up with negative signs, right? They ended up being minuses. The thing in the numerator ended up being positive. And then if you had done this version here, you would have the exponents, and it would just be, oh, the 1/2 gets brought down for the x, and then it's positive because it's in the numerator. And then for these guys, the exponent gets brought into the front, and they're negative, and they're in the denominator. In fact, they are negative because they're in the denominator. So whenever you split things up, when you go to do this minus the denominator being split up part, you'll end up distributing negatives so that anything that's in the denominator ends up with a minus sign in front of it. And anything in the numerator will end up with a positive sign in front of it, or nothing in front of it, because it assumes it's positive. We can formalize this and then use it to our advantage. So when we go to do this problem here, I want you to keep in mind that if it's in the numerator, if the factor is in ... the numerator, then it's positive. or a plus sign. If it's in the denominator, it's going to be negative, or there'll be a minus sign in front of it. And then the other important thing we're going to be doing here is remembering to bring down the exponents. All right, so the first thing I'm going to do, I want to make sure everything is written so that it has an exponent. So troublemaker is this guy right here. The cubed root of z squared. If you remember way back here, I wrote that if you have if you have the nth root of x to the m, it gets written as x to the m over n, so the power is in the numerator and the root is in the denominator. Well, we can do that here. So this is the same thing as z raised to the power in the numerator, root in the denominator. So z raised to the 2/3. So I have log base 5 of y to the 4th over x, and then z raised to the 2/3. Now I'm going to do this in one step. There are 3 factors. So we have one factor here, one factor here, and one factor here. Remember, factors are going to be things that are separated with multiplication or division. Technically multiplication, but in this case, the division idea works. All right, so because I'm not going to have enough room here, I'll bring it down to the next line. Y to the 4th is in the numerator, and he has an exponent of 4. So he'll be positive because he's in the numerator. He gets the 4 out front, and then log base 5 of y. X is in the denominator. He doesn't have an exponent to bring down, so I don't have to worry about that, but I'll do a minus sign because he's in the denominator. Log base 5 of x. For z to the 2/3, he's in the denominator, so it'll be a minus. And then we'll bring down his exponent, so 2/3, and then just log base 5 of z. And that's our final answer. So let's go even crazier here. I'm looking at this mess, so I'm not even going to read it out loud. It's a mess, right? The only kind of setup thing we need to do here is rewrite the radical as an exponent. So it's 2x plus 1 raised to the 1/2 because it's a square root. So we can just kind of ignore that guy. And now we have 1, 2, 3, 4, 5, 6 different factors that we're going to separate it into. So there's going to be 6 different ln pieces down here when I separate this. I'll start here. So it's in the numerator, which means it's going to be positive. And then he has an exponent of 2, so I'll bring the 2 down in front. He gets an ln, and then the base is x. For my next one, he's in the numerator, so it'll be a plus sign. And then there's no exponent to bring down, so I won't put anything in front. And then it's just ln of x minus 7. I do want to take a moment right here to talk about ln of x minus 7. Parentheses are incredibly important. I'll write it. Parentheses are important. So, especially with logs, if we had written ln of x minus 7, this would not mean ln of x minus 7. So these meanings are not the same. Instead, if you write ln x minus 7, this is interpreted as ln of x minus 7. So telling the viewer of your homework or your tests that something is completely inside and you need to do it with parentheses. That that's what indicates where the inside starts and ends. So if there aren't any parentheses, you just assume the thing right next to it is the only thing on the inside. So very important. All right, let's go back to here. So it's in the numerator. This factor's in the numerator. So we will do oh no, I lost my color. Hold on, guys. All right, I think I got a color that's, oops, relatively similar. Close enough. Anyway, so he's in the numerator, so it's a plus sign. His exponent is 1/2, so I will put the 1/2 in front. Then ln of 2x plus 1. Moving to the denominator, so this factor here is in the denominator, so he'll get a minus sign. And then the exponent is 6, so we put the 6 in front, and then ln of x plus 1. Let me take this guy and, sorry, let me take this guy, move him down there so I have more room. All right, next factor is this one. It's in the denominator, so it's a minus sign in front. His exponent is 2, so we'll bring the 2 in front. Then it's ln of x minus 1. Our last one is in the denominator, so it's a minus, so this guy right here. There's no exponent, so I don't need to worry about bringing anything in front. And then 4x minus 9. And in one step, we have expanded the entire thing. This is a skill that will come very in handy once you're in calculus. I promise you this is an amazing skill. If you're able to do this in one step, you will save yourself a lot of time in calculus someday. So I know it looks scary, but it honestly doesn't take that long, especially once you have this trick under control. So let's do this next one very quickly. In fact, I encourage you, the viewer, to pause and try this one on your own. I'm going to show you how quickly this can be done and how it really should be. The first thing I'm looking at is this 4th root of x to the 5. That's the same thing as x raised to the 5 over 4. And then I'm just going to start breaking stuff up. So my first factor, positive, and then exponent is 2. The inside part is 3x minus 1. The next factor is in the numerator, so it's positive. The exponent is a 5 over 4. And then the inside part will be an x. Next factor is in the denominator, so minus sign. 3 is its exponent, ln of x plus 7. Next factor is in the denominator, so it's a minus, and then no exponent, so we don't need to put anything in front, and then x minus 6. And that's our answer. So that's expanding logarithms. Now, we can also go the opposite direction and take something that's fully expanded and combine it together into one single logarithm. And that's another important skill. So let's look at doing that. So combine into a single logarithm without negative exponents. So we can do this step by step if we want. We could start with taking this 1/2 and bringing it up as an exponent, bringing this 2 up as an exponent, because we're trying to go and make it into one singular logarithm. So we'd have log base 6 of x to the 1/2. And then we'd have plus log base 6 of x minus 2 raised to the 2. Now that there's nothing in front of the logarithms, we can combine them together so they are addition on the outside, which turns to multiplication on the inside. So, and they have the same base, which is important. So log base 6 of x to the 1/2 times x minus 2 quantity squared. And that's about as combined as it can go. If you wanted to be really fancy, you could change this x to the 1/2 into the square root of x. You know, just to show off your math skills a little bit. But that would be our answer. Let's try another one. So once again, we're going to start with bringing up the exponents. That's a good place to start. The w, the log base 2 of w, doesn't have an exponent, so I won't deal with that. So we have log base 2 of y to the 1/4 plus log base 2 of z squared minus log base 2 of w. I will start by combining these guys together. So it's addition on the outside turns into multiplication on the inside. So I'm just doing these two to begin with. So log base 2, we're going to multiply those together. So y to the 1/4 times z squared minus log base 2 of w. We're now looking at the situation of subtraction on the outside. So subtraction on the outside turns to division on the inside. So log base 2, y to the 1/4 over z squared, or times z squared, all over w. And that's done. If you wanted to be fancy, once again, you could write that as a radical. So you could say the 4th root of y times z squared all over w. And that would be a correct answer too. But maybe what you notice here is that this doesn't need to be done in that many steps. Just like we can expand a logarithm in one step, we can combine a logarithm in one step too. The important thing is that the numbers, that I had my pointer, the numbers out front become the exponents. And if there's a positive sign, it goes in the numerator. So these guys are positive, they went in the numerator. If there's a negative sign, it's going to go in the denominator. So let's practice this. Right? If there is a I'm going to write down here, if it's a positive sign, it goes in the numerator. And then if it's a negative sign, let's use pink. No, we'll use red. If it's a negative sign, it's going to go in the denominator. So this guy right here has a negative sign in front of him, which means he's going to go in the denominator. This next piece has a positive in front of him, so that's going to go in the numerator. This guy has a negative in front, so that would be a denominator. And then both the next terms have positives. They have plus signs in front of them, so those will both go in the numerator. Now, the inside of the logarithm, we just have to worry about putting up the exponents. So if there's a negative in front, don't use the negative when you bring up the exponent. The negative part is being taken care of by moving it to the denominator. So you don't bring the negatives into the exponents at all. Don't worry about that. You would just take the number and bring it up. So this guy is going to get the 2 brought up. Then, let's see, this guy will get his 3 brought up. So we're going to do it in one step. And here's how it's going to look. It's going to be a log base 3. Then I'm just going and looking for the things in the numerator. So this part, and this part are in the numerator. This guy had no exponents to bring up, so we'll just write this factor down. So that's x squared plus 4. This one, the 3 will come up and you'll have an x cubed. So there's an x cubed here. This one right here, there's no exponent to bring up, so it'll just be an 8. In the denominator, so this guy here is in the denominator. Don't worry about the negative. The negative just tells us that it goes in the denominator. The 2 comes up, so you'd have an x squared. So there's x squared. The other thing in the denominator is this guy here. So the inside is a 6. There's no exponent to bring up, so it'll just be a 6 in the denominator. And there it is. Now, this isn't actually fully simplified because some things can simplify a bit. Let's go ahead and do that. But it is combined. So I'm going to rewrite this a little nicer. So 8x cubed times x squared plus 4 all over 6x squared. So the top and the bottom are both divisible by 2. So this would become a 4. This would become a 3. And then x cubed over x squared. That's going to be x to the 3 minus 2, which is just x to the positive 1, which is x. So it ends up simplifying so that this x cancels completely. It cancels that exponent out. And we have log base 3 of 4x. Oh, and it's not going to be a fraction anymore because we canceled the whole denominator. So the whole denominator besides the 3, but we'll just write it like this. So 4/3 x times x squared plus 4. And there it is. I promise we are getting to the end now. I want to do one more of these combining ones. I just want to show one more thing. If we're looking at this guy, it's only slightly different than the other one because it has this 2 out here and then there's stuff going on. All you have to do that's different is just distribute the 2, just like you would with, just algebra. So the 2 gets distributed first. So I have 4 log base A of 5w plus 1 plus 1/5 log base A of w plus 8 plus 2 log base A of w minus, now this will be 2 times 3 because it's 2 times 3. So minus 6 log base A of 1 minus w. And now things that go in the denominator are going to have the minus sign in front of them. So this is the one that would go to the denominator. Everything else has a positive in front of it. So those would all go to the numerator. And then these exponents will come up top here. So we have log base A. In the numerator, we have 5w plus 1, and then his exponent becomes a 4. For the w plus 8, he gets the exponent of 1/5. And then we have a w squared. In the denominator, once again, don't worry about the negative sign, just bring the 6 up. So the factor is 1 minus w, and then he gets an exponent of 6. And if you wanted to make this really fancy, you could turn this into the 5th root of w plus 8, but, just good circling it and calling it there. So there you go. That's expanding and combining logarithms. The most important thing from this section, I would say, is expanding and combining logarithms. So definitely practice those ones. The last thing we're going to do here, I'm going to do some true or false. Now, I would like for you at this time to pause the video and guess true or false. Don't guess. You use the noggin. Think true or false. Decide whether these are true or false. Go ahead and pause it now. Okay, so coming back, I'm hoping that you have written down the true or false parts, and I will talk about whether these are true or false. This first one is false. So what is true is that division on the inside turns into subtraction on the outside. So log x minus log y, but it won't turn into division log x over log y. These are some very common errors here, so it's worth talking about. All right, this next one looks like we just took the log base 2 and split it up over them, and we can't do that. That's a false right there. So what is true, if you had division, you can separate it into subtraction, but you can't just separate the log base 2 like that. For this next one, this one's true. It's just that's how you would expand the logarithm. Part D, this one is true. It's just one of the rules. You can bring the exponent down in front. E is false. So notice that this is a log multiplied by a log. It's not two things inside of a log being multiplied. It's a log multiplied by a log. So what is true is that if you had log of p times q, this would be equal to log p plus log q. But when the logs are multiplied together, that doesn't work. Okay. F is false. It's once again a situation of up here, part A. It only separates into subtraction if its inside is being divided, so x over y on the inside of the log. And G is false. So this is false because the exponent is on the outside of the entire logarithm. So you can't bring the x down in front if it's outside of the logarithm. If I had instead wrote log base 2 of 7 to the x, it's assumed that the 7x is inside the logarithm. It's assumed that you're doing this. So you could bring the x down in front. But you're unable to do that if there are exponents showing that if there are parentheses showing that the exponent belongs on the outside. So, common errors. That's about it for this video. I know it's a long one, so I appreciate you, the diligent viewer who got to the end of this. Hopefully that helps a little bit. I know that those shortcuts are really useful, so hopefully it was informative. I hope you're having a fantastic day. You're working hard. Keep at it. Keep doing what you're doing. You're doing awesome, and I will see you in another video.